Hello everyone. My name is Oren and I'm a scientific computing researcher from Stanford and the Technion. In this talk I would like to tackle the challenge of texture boundary detection in metallography. Specifically, we will talk about how a context-rich segmentation can be designed to outperform traditional models on fine-grained texture-based tasks, which one of those is metallography. So, in general, our goal is to enhance boundary detection within metallographic textures to improve our understanding of microscopic material properties. Automated texture analyses play a critical role in material science, enabling precise, scalable insights that are essential for evaluating and optimizing performance in real-world applications. From bridges to aircraft, these insights directly inform the design and integrity of critical infrastructure, and better boundary detection brings us closer to that reliability. One of the key goals is to approximate grain boundaries in metallography accurately, which is challenging due to the intricate and often ambiguous nature of texture-defined boundaries. Unlike clear object edges in natural images, these transitions are subtle and often gradual, requiring models to detect nuanced variations in texture rather than shape. Traditional segmentation models often struggle because there are no clear object edges, only gradual transitions in texture. This ambiguity makes it difficult even for experts to agree on ground truth, which further complicates both training and evaluation. We elaborated on this topic in a previous 2023 in Europe's Machine Learning for Physics paper. Current state-of-the-art segmentation models, like the Segment Anything model, are not designed for pure texture images. They rely heavily on semantic cues, object shapes, and prompts, none of which exist in metallographic textures. As shown here, some fails to capture meaningful grain boundaries, even when trained or prompt, reinforcing the need for models specifically adapted to texture-based segmentation in microscopy. We elaborate on such training in our scientific reports paper from 2022. So, to establish common grounds, we introduced in 2023 the Texture Boundary in Metallography, or TBM for short, dataset, as a primary benchmark for our research. This dataset is designed to be as general and unbiased as possible, with expert-verified annotation that aligns specifically with the task of texture boundary detection. It provides a robust foundation for evaluating models in microscopy, and particularly in metallographic analysis, where clear object boundaries are often absent. MLOgraphy was one of our earliest methods for detecting grain boundaries in metallographic images. It used a unit trained on 128 squared fully annotated patches, focusing only on the manually labeled areas. While this approach produced clean predictions, it has a major limitation. The model saw only local context. As a result, it often failed to generalize across broader texture variations or capture long-range texture transitions, both of which are essential in metallographic analysis. As shown here, the result required extensive post-processing, including binarization and watershed contouring, to produce complete boundary maps. This dependency increased the risk of overfitting and limited the model's ability to generalize to new textures. This is why we recently introduced MLOgraphy++, an enhanced version of MLOgraphy that uses larger, partially annotated 320 squared context windows. By applying the loss only to annotated pixels while preserving background context, the model learns broader texture relations, significantly reducing the need for post-processing. This design allows the network to better distinguish true boundaries from noisy textures, by leveraging more spatial information during training. In partnership with Clemex, the MLOgraphy++ algorithm was introduced to Clemex Studio, a no-code platform for developing segmentation algorithms using partial annotations. The platform offers a streamlined workflow, allowing users to upload images, annotate them, and train segmentation algorithms based on partial annotations. Here we see an image from the TBM dataset with partial annotations added in the Clemex Studio system. This semi-click segmentation method is used to label the grains, providing context for further segmentation training. You can see the results after training is complete. The predicted grain boundaries that are shown on the right demonstrate the effectiveness of the model after iterative refinement with partial annotations. Now we can compare MLOgraphy with MLOgraphy++. MLOgraphy++ captures finer and more accurate grain boundaries, thanks to partial annotation and larger context. Zoom-ins show how it aligns better with the actual texture. Usually, the Heyn intercept method is used to estimate average grain size by counting how many times test lines intersect grain boundaries. It's standardized under ASTM E112 and is still commonly used due to its simplicity. However, it has several limitations. It assumes grain boundaries are fully visible, which is often not the case in real samples. It also struggles with irregular or incomplete edges, and its accuracy depends heavily on the placement of test lines. As a result, it can underestimate grain size when boundaries are ambiguous, fragmented, or when grains are not well defined. This motivates the need for more robust, automated approaches, especially for modern metallographic datasets. Here, the classical Heyn intercept method is applied to a sample image. The figure shows grain size measurement representing intercept counts along test lines and the average grain size. Instead, we developed a variation of the classical Heyn intercept method, which we called Heyn compare. Instead of simply counting intercepts, the method measures the average distance between them along fixed horizontal lines. This makes it more robust for real-world images, where grain boundaries are often incomplete or irregular. By using distances between intercepts rather than assuming closed contours, we can extract more accurately grain size estimates, especially when boundaries are fragmented or partially annotated. This method is particularly useful in automated pipelines and helps bridge the gap between traditional analysis and modern imperfect data. Here you can see the Heyn compare method applied to a cropped image from the TBM dataset using horizontal lines to measure the grain boundaries. So now we can create a direct comparison between MLOgraphy, MLOgraphy++, and the ground truth using our Heyn compare method. Each crop is 256 squared pixels, and the red lines represent the fixed test lines used to calculate grain size. On the left, we see MLOgraphy predictions. Many boundaries are missed or fragmented. In the center, MLOgraphy++ shows clearer and more continuous grain boundaries, closer to the ground truth on the right. This visual comparison highlights the MLOgraphy++ better alignment with the true grain structure, improving measurement reliability. These graphs show the grain size distribution for individual crops, computed using the Heyn compare method. On the left, we compare MLOgraphy and MLOgraphy++. While both methods follow a similar trend, MLOgraphy++ consistently produces grain sizes closer to the expected range. On the right, we see that MLOgraphy++ aligns very closely with the ground truth, demonstrating its improved segmentation accuracy. Importantly, MLOgraphy++ achieves this performance without any post-processing, thanks to its use on partial annotations within larger context windows. Sorting the grain sizes also help identify outliers, which is essential for understanding critical deviations in material behavior, something traditional methods may miss. To further enhance our results, we fine-tuned AutoSum, a well-established model similarly to the MLOgraphy method, to explore its potential for future work. AutoSum replaces manual prompts in SAM with an automated encoder for fully automated segmentation. It was trained on 256 squared fully annotated TBM crops for 100 epochs with augmentations and post-processing. We found it interesting that AutoSum demonstrates strong segmentation performance, even with intricate and fragmented grain boundaries. Although the IOU and dice scores are relatively low, reflecting the limitation of these metrics on complex structures, the n-compared grain size show that AutoSum's output is very close to the ground truth. This indicates that the traditional metrics may underestimate the model's actual effectiveness. AutoSum achieved a mean grain size comparable to the ground truth, highlighting a strong match. These results suggest that with further fine-tuning, SAM-based models can be adapted effectively for metallographic segmentation tasks. But the problem is that standard SAM models are trained on datasets focused on clear object boundaries, not subtle textures. This makes them biased towards shape-based segmentation and less effective in domains like metallography, medical imaging, or remote sensing, where textures are critical. As seen in the examples, SAM struggles to capture fine-grained patterns, highlighting the need for adaptation in these textual domains. To address SAM's limitation in texture-rich domains, we fine-tuned state-of-the-art SAM2 on the 8020K datasets using texture augmentations. This encourages the model to focus on texture patterns rather than just object shapes. Over time, with controlled augmentation strength, the model shifts from semantic segmentation to a more texture-aware approach, shown here by the improved alignment with ground truth. Here we apply texture augmentation to 8020K using textures from the DTD dataset. By adjusting the augmentation parameter, we control how much texture replaces the original content. Low augmentation parameter values keep the semantic structure intact, while high ones fully replaces instances with texture. This gradual shift helps teach the model to rely on texture rather than object shape during fine-tuning. Eventually, we evaluated the model on the real-world texture dataset. The top row showed the original images. SAM2 variations struggle. They often segment by color patches or grid-like blocks, but fail to group texture coherently. In contrast, texture SAM correctly segment regions based on consistent texture, even when there is no semantic object boundary. You can see that its predictions closely match the ground truth, especially in cases like the cobblestones, tiles, and textures on the left. This shows texture SAM strength. It's not just segmenting shapes, it's learning to understand and follow texture changes, which is critical for domains like metallography or material science. Building on the texture-focused fine-tuning from 8020K, the next step is to apply SAM to real metallographic images across multiple material classes. This will allow the model to learn the unique texture patterns found in metallography, beyond semantic segmentation. Fine-tuning on diverse metallographic datasets will broaden SAM's ability to generalize across different microstructures, bringing us closer to segment anything in metallographic images. So, if you find this line of work interesting, have new ideas on how to promote this from either the AI or data paths, please contact us. We're looking forward to collaborate with universities, laboratories, and other companies to make this work into real production. Thank you very much for listening.